next speaker is Ben Ofori-Okai. He's an associate scientist working at the SLAC National Accelerator Laboratory. He received his BS in chemistry from Yale University in 2009 and his PhD in physical chemistry from MIT. Currently, Ben is taking the spectroscopic tools he learned and developed and applying them to investigate materials that have been driven far from standard conditions, temperatures on the order of 10,000 Kelvin and millions of atmospheres of pressure. Ben, thanks for being here.
Cool. Am I on? Can people hear me? Great. So thanks a lot for that introduction. It's really been a humbling experience to be part of this class, this Talented 12 class of 2023. And I'm really excited to tell you about some of the details of this work that I've started, first as a graduate student through my postdoc and now continuing at SLAC. And so I'm going to start this talk in one area or in one topic that you probably never thought you'd hear about at an ACS meeting, which is the Earth's magnetic field. Humanity's known about the Earth's magnetic field for over 2,000 years, almost 4,000 years. We've known about it because we've used it for navigation. We know about it because it protects us from cosmic ionizing radiation, which helps make the Earth habitable. But it turns out that with all these things that we know about it, there's a lot of things that we don't know about it. Among which are the fact that we know that the Earth's magnetic North Pole has been moving at least over the last 120 years. We know that over the course of Earth's history that the North Pole and the magnetic North Pole and the magnetic South Pole have shifted positions entirely. But we don't really understand why. This is sort of an open question in geochemistry, geophysics. We still care about the Earth's magnetic field because, again, it keeps us alive. It helps us navigate, maybe not as well as GPS, but as sort of a fallback plan, we can use it. And so there's theories, there's open questions about the source or the origin of the Earth's magnetic field. And understanding that requires understanding this theory called the dynamo theory. And one of the parameters that goes into this theory is the electrical conductivity of a material. And so sort of boiling it down, one of the things that we need to know to be able to predict how this theory works is the electrical conductivity of materials at the center of the Earth and conditions found at the center of the Earth. And this is a really challenging state of matter to probe. So this is sort of like a plasma condition, a dense plasma. And this is, again, an active area of research in a bunch of different communities. So we have tools, it turns out, to create conditions that are similar to those that are found at the center of the Earth, some of the most exotic conditions that you can find in the universe. So this is a photo of the Matter and Extreme Conditions end station, one of the end stations at SLAC's Lynette Coherent Light Source, where we use really high energy, high intensity lasers to create some of them are conditions that mimic some of the most intense conditions, again, that you'd find in the universe. And so this sort of gives us the tool that we need to create these exotic environments. And at this point, I've sort of talked to you about this sort of interesting problem, this interesting exotic part of the universe, and you might be asking yourself, why is a chemist involved in this discussion at all? Why is this happening at an ACS conference? And it's a great question. I hope to be able to answer that question over the course of the next few minutes. But for me, where it starts actually is not with me. It starts a little bit before me, or many, many, many years before me. So it starts in this country, Ghana, which is where my parents are from, in West Africa. My dad is from this region called Piki. My mom is from this region called Kwehu. And they were born in the late 40s, early 50s, before Ghana actually was an independent nation. And so by the time that they reached college age and they wanted to go attend a university and improve their education, there weren't that many options to them. They're actually older, I believe, and the internet will fact check me on this, but I believe that they are older than the oldest university in Ghana. And so they decided that what they would do is they would be intrepid and brave, and they would move to Germany of all places. First studying in Darmstadt, and then eventually moving to Berlin, where my dad actually got his PhD, also in chemistry. And this is a photo of them that I found digging through old albums in my house. And life tip, if you can find somebody who looks at you the way my dad is looking at my mom, I think you're doing pretty well. But I throw this up there because I found, and I still think about the fact that they were very brave people. They tried doing something that was completely foreign to them and where they didn't, being sort of far outside of their comfort zone. And so that's sort of part of why I've wound up where I am and why I'm on the stage here today. So more directly, or I should say then also that as they raised me to be curious, they raised me to be not afraid of asking questions, trying things that I never thought that I could do. And so I thank them for that. And also to be brave and try things that I didn't think that I wasn't going to be able to do. So more scientifically, where does this start? Well, for me, it starts actually at Yale University, working in the lab of the late, great Professor Charlie Schmutmeyer. This is us in 2008 when I was an undergrad, when we'd just gotten our new set of lab goggles trying to look cool. And I met Charlie, he was my PChem professor, and I had to pick a research project for my senior thesis. And I like Charlie, he's kind of a fun guy, a little awkward guy. And the thing I knew about him that he was working on was this thing called terahertz spectroscopy. And the thing I knew about, and I put up terahertz in the electromagnetic spectrum in various units depending on how you like to think about light. And the thing that struck me was this 33 wave numbers unit, because what I knew as an undergraduate who'd taken organic chemistry was that 33 wave numbers was far in the fingerprint region, and everything in the fingerprint region was a disaster zone. There wasn't anything useful that you could learn in the fingerprint region. But here was this guy who I happened to like a lot and I respected a lot, and he was spending a lot of time studying things in the fingerprint region. And so I approached him, I said, hey, I want to work in your lab. He first said no, and then he said yes. I finished the PChem class, and then he said yes. And what I came to learn is that what he was studying intermolecular vibrations and the relationships between those two. And so as an undergrad, I got to start studying these sorts of spectra. So these are examples of terahertz frequency spectra of D or L valine, and then racemic mixtures of the two in crystalline form. And if you take away nothing else from this slide, the thing that I want you to realize is that nominally these molecules or these crystalline systems are similar or almost identical. And besides, with a couple of very specific exceptions, spectroscopically they're basically identical. But the terahertz spectra can differentiate between these three cases very, very easily. Right, so this is an enantiopure crystal, and these are racemic mixtures. These two different racemic mixtures have crystallized into different structures. We actually discovered this because I had made a racemic mixture in the lab and crystallized it, and we measured one spectrum. And then we bought the racemic mixture from Sigma, and it produced a different spectrum. And we realized, oh, there's two different crystalline polymorphs, and we can see them both really easily. And so this was really cool. I thought, oh, here's this nominal region of the fingerprint region where it was impossible to learn anything, and here we were learning really fundamental things about the interactions of these molecules and how they give rise to these intramolecular and intermolecular vibrations, which are characteristic of intermolecular interactions, these van der Waals interactions. And so I thought this was really interesting. I decided after I graduated that I would go on to grad school. I tried really hard to leave terahertz spectroscopy, but I couldn't. And in doing so, I wound up learning that, in fact, in addition to studying intramolecular and intermolecular vibrations, you could also study spin and magnetic transitions in things like transition metal complexes or magnetic materials, but that you could also use it to study the electronic structure and the electronic properties of materials. And so one thing that I've come to realize that makes terahertz spectroscopy useful as a tool is that if you wanted to characterize materials, for instance, if you wanted to determine whether or not something is an insulator, a semiconductor, a metal, or a superconductor, terahertz spectroscopy is a really great way to do this. One example experiment where this is possible is the case where I'm illustrating here, where you have a short femtosecond pulse laser that you're using to heat up a sample or deposit energy into a sample. And then I'm going to measure this sample with a terahertz pulse that's very, very short, on the order of about a picosecond or so. And you're going to measure how the sample changes, how its electronic properties change. And in this case, what we're seeing is a change in the resistivity. So it goes from being semiconducting. Right when the laser arrives, it switches and it becomes metallic. And it's during this transition time that we're saying, oh, it's sort of transitioning between these two states. And this transition time is on the order of a picosecond. And for calibration, a picosecond, right, is about a millionth of a second. So we're seeing these, you're sort of time resolving this transition between these two different states, between having states of low electron mobility and high electron mobility on really fast timescales. Now, this is important because, or at least it's important for me, in part because when I finished my PhD and I was looking for a postdoc, I was contacted by a professor at SLAC who said, hey, I really want to make terahertz measurements of materials at the center of the Earth. How can we do that? And there was a challenge, which is that this measurement actually takes about 10 or 15 minutes to do. And integrating it with a measurement where we're trying to study these extreme conditions has a problem, because the way that you do one of these extreme conditions experiments is you take a sample of a material that starts off as a solid, like a hunk of aluminum, let's say. You heat it with a laser on the order of about a picosecond or so, to the state where the temperature in the order is on the order of thousands to tens of thousands of degrees Celsius or Kelvin, densities on the order of 1 to 10 grams per cubic centimeter, and a lifetime on the order of about 10 picoseconds to a nanosecond. And afterwards, you lose the precious sample, you lose the thing that you want to make this measurement of, and so you have to capture all of the information that you need in this time scale of about 10, a picosecond to nanoseconds, and you only have one shot to do it. And so over the course of my PhD, I managed to figure out a way to make these single shot measurements. The details of it look something more like this, where this is the inside actually of that same vacuum chamber that I showed you a couple of slides ago, where we set up an experiment to drive a sample, again, to these really extreme conditions. The sample actually sits right around here, and all of this is optics that are designed to get the lasers into and out of the sample. And then we can probe the properties in that state. And so this is an example of sort of what some of that data might look like. Where here, these are measurements that we did on some aluminum. And we've taken the aluminum from room temperature roughly to about 6,000 degrees Celsius. 6,000 degrees Celsius is about the temperature you'd find at the center of the Earth. And here we're extracting the electrical conductivity, this important parameter that we need to understand dynamo models. We see that there's this massive drop in conductivity, so we're starting to, at the very least, be able to, although aluminum is not found at the center of the Earth, we can at least reach similar conditions and start to make measurements of very fundamental sort of material properties on this material. Now, to wrap up, I want to try my best to link this back to the spirit, or the chemistry community, which is, and the way I'm going to try and do this is by highlighting the fact that there's a bunch of sort of simple materials that we think we understand, simple molecules that we think we understand the properties of at STP. So iron nickel alloy, water, although some people argue water is the most complicated molecule ever. Polystyrene, we've heard a lot about polymers and polymer chemistry over the last couple of talks. But it turns out that these materials on their own actually wind up being really good analogs for the center of planets all throughout our solar system. So the center of the Earth is mostly iron and nickel. It turns out water is a really good proxy for understanding the mantle of Uranus. There's a lot of hydrogen and oxygen there, and it separates into this super ionic phase of water that we think is responsible for the generation of Uranus's magnetic field. And polystyrene, it turns out, is a good approximation for, or when you compress it, it becomes a good approximation for the mantle of Neptune, because that's mostly methane. And in this case, what you see is that when you crush it, it turns into diamond, and the hydrogen sort of separates out. And I think what's been really cool for me and talking to my colleagues is that in this particular case, there's chemical intuition and chemical understanding about the bonding and how the bonding is going to change and evolve as you go through these high temperature extreme phases of matter that are maybe not so obvious to one set of communities, but is something that we can talk about pretty easily based on our own experiences. And so I think I'll just jump to the end in the interest of time, and I want to thank everybody who's been involved in all of this work. Again, starting with Charlie's group at Yale through MIT and through the High Energy Sciences at SLAC. This is far from an exhaustive list. I've tried to do the best that I can to capture mentors, senior grad students, fellow scientists, grad students, and undergrads that I've worked with. And so again, thank you to the C&E News team, the ACS, for nominating me, for including me in this cohort, these people for funding, you for your attention, and I'll take any questions.
That was a great talk, Ben. Quick question. So you were talking about the time scale of this terahertz measurement. I was curious if it's possible to couple this measurement with some imaging and to have some spatial information. If so, what would be the resolution of the spatial resolution?
So that's a really great, so your question's about spatial resolution of a terahertz measurement.
That's right.
So that's a really great question. And to first order, you'd think that it's probably limited to the order of the wavelength of the light that you're using. But I know that there's a group that has done basically terahertz enhanced scanning tunneling microscopy. And so then you're limited to whatever, at least I don't know that you get the same specificity that you'd get out of a terahertz measurement, but you are using, I think, the terahertz field as sort of like a gate in your STM. And so you get some enhancement of the resolution that way, and then the time scale is still limited to the picosecond time scale. But yeah, you do get enhanced spatial resolution that way. Otherwise, you're limited to order a few hundreds of microns, unless you can couple that with some other, again, optical probe. Actually, there's other thoughts that I have about that I'd be curious to talk about if you wanted to talk about it. But yeah, it's a great question, so thanks for that.
So when I was reading through your profile in the magazine, it also mentioned that you're starting some work on plasma. And I was curious, what's the most biggest interesting question people are asking you about plasma and asking you to work on?
That's a great question. So I think, in sort of the plasma physics community, I think there's a really growing interest in understanding non-ideal plasmas, so dense plasma. Most of the plasma, when most people talk about plasma, they're actually basically thinking about ionized gas, right? And so it's only interacting through collisions in the same way that like an ideal gas does. And otherwise there's some like charge-mediated interactions, so some sort of Coulomb interactions. But these dense plasmas, which are actually, again, sort of found, like they would describe sort of what's happening at the state of the center of the Earth, is something that is really not super well understood. Again, because these states are super exotic and super extreme, it's hard to go in and make any kind of measurement there. So electrical conductivity is one. And the other thing that people are interested in, and the other reason people are interested in this, is because the idea, or the plan to develop like fusion reactors actually requires building or exposing materials to these extreme conditions. So there's been a lot of reports recently about the National Ignition Facility and the work that they're doing on trying to achieve fusion. Again, actually conductivity winds up playing a pretty important role in that. And so that sort of is an interest, that's like an area of interest in that community as well.